Today's topic is very specific, focused on the coherent gravity design method for reinforced soil structure. Before I go into the core subject, into the design methods, I am going to share a little bit about the history, a little bit about the introduction, and a recap of the concept. I hope that will help you again to understand. I'm sure you all already know the subject, the background, but just to give a small recap, and then I will go into the main subject, starting with the type of reinforcement, details about reinforced wall, design references, how it started, then the design methods, how the coherent gravity method has been evolved, and it has been, I would say, the method which has developed maybe 60 years back, and we still follow the same method. External stability, then I'll go into the internal stability, and sorry, it's conclusion. That's the geotechnical problem. So the last part is the conclusion. I'll just give a small rebriefing. So coming to the introduction part, the background, I'm sure a lot of you know this story about this invention, which happened in 1957, and there is a nice small story. Probably you have heard. If you have not heard, I'll just repeat it again. It's one, when the person named Sir Henry Vidal, by profession he was an architect, and he was actually in a beach called Ibzia in Spain, and he was actually seeing the children playing and making sand castles. Sometimes we have all played. If you add little bit of water, the pseudo cohesion allow you to build sometimes small castle. But when the size of the castle is big, it's not easy to build just like adding water. So the children used these needles, pine needles, to build this castle, and that's how the idea stuck, and that's how the entire invention and the technology has evolved after this idea. So it's a very simple idea, and I'm sure historically, if you see a lot of structures which are built using the same concept. So that's how it started, and I think Henry Vidal, he started research on this subject. He graduated from this University of Ecole, and in 1961. And after 5 years of establishing the theory of his process and experiments on scale model, he filed his patent of reinforced earth in 1963. And the first reinforced earth structure was built in 1964, as you can see in the right-hand side corner. At that point of time, the facing was using steel. It's a steel plate, actually, in a U-shaped plate, and it's about 3 millimeter thick. At that point of time, it was not galvanized, and I'm not sure whether you know that it was using steel with smooth finish. That means it's just a steel strip with no ribs or anything. So we used to call it a smooth strips. And that's how the first structure was built. In fact, behind the scene, I am not sure whether you are aware, Henry Vidal, the first idea actually to build a wall was not with steel. It was actually synthetic. In fact, he built a small scale wall using, that point of time there was no polyester, so he used nylon. But the nylon, because the life of the nylon is not longer, so he gave up the idea of using synthetic, and then he started thinking about steel. And that point of time there was a lot of data available on corrosion from the steel pipe industry. The oil industry had got a lot of large data, how steel behaves under soil, and that data he used to actually convince different authorities and start building and start his research program on this subject. So this is a little small background, and just to do a little bit of marketing, I would say. And the logo that came up, what you see is basically the soil particles. And the concept of soil reinforcement is well explained in the picture. On this top middle picture, you can see the stones which are very rounded, and this vertical structure was built using this board. It's a small board, and that friction between the boulders allowed it to stand vertically. Now, sometimes I have asked that how this concept applies to a soil. I mean, it's boulder, it is very well understood. I think the concept very well applicable for soil as well. And I have collected this small video. Sand actually can be reinforced. That was the video. Unfortunately, it's not working. So I'll see if I can come back to that. And that concept has been converted into a concept of reinforced soil wall with reinforcement and with a facing element. The facing element is just an skin, and the entire soil mass reinforced with soil reinforcement act as a gravity structure. So that's the basic background about the reinforced soil. And we'll talk about coherent gravity method. So the coherent gravity method is applicable for inextensible reinforcement. So as on date is the steel, which is known as inextensible reinforcement. There are some discussion, some research still going on whether some of the synthetic reinforcement can be categorized into coherent gravity method or not, but it's still not concluded. So I'd remain my presentation only around using reinforcement using steel strip. But you can see with the steel strip also there are various variant of reinforcement that is possible, even using steel bars, as you can see in the bottom, which we call them ladder reinforcement. So some people uses a ladder, some like us uses steel strip with ribs, and there can be several dimensions. The typical dimension that we use is 50 by 4 millimeter thick, can be 40 by 5, can be wider also. Some people use 60 millimeter by 4 millimeter, but generally not less than 4 millimeter because of corrosion issue. And also it is not easy to manufacture within the tolerance less than 4 millimeter. So that's the reason the minimum thickness of the steel is 4 millimeter, but it can be thicker also. So I'll come to the reference of about the history, how this method has been evolved. The first international reference, of course, published in France. It is on the left-hand side, and the steel translation on the right-hand side. It was done in 1979. This is a detailed guideline on reinforced soil structure issued by Ministry of France, and it is there till the next published code, which came out in 1991, which is the French AFNOR code. And then 1995, the British code came up, and this is the today's list. We have several design guidelines, and this method has been accepted in almost everywhere in the world. I will be focusing my presentation around British guideline, although the principle of coherent method is more or less same. A slight variation here and there is there in other international guidelines, but the principle is more or less same. So I will more talk about the principles and then very briefly on the design steps, rather than going into different codes. Even then, I'd like to highlight that there are British code, there are recently published, British updated. You have FSW, you have ASHTO, which is always upgrading themselves. And then IRC 102 is there. And then you have AFNOR, which is the French guideline. And there are several other, Hong Kong guideline is there. But in India, these are the three main, I would say, international, British, ASHTO, and AFNOR, that is acceptable, I would say. And in practice, it is only British and AFNOR. And of course, now the IRC, we are all following the IRC guideline. The concept is more or less same. So the two design methods, which is well accepted internationally and in India as well, is the coherent gravity design method and tieback wedge method. So the coherent gravity design method, as of now, is defined applicable for inextensible reinforcement where the strain is less than 1%, and cannot, that means the behavior of the structure is slightly rigid in terms of its deformation, and that's why the earth pressure coefficient is not constant. And in the tieback, no post-construction movement is just a, I mean, because of the steel, generally the post-construction movements or deformations are less, but in general it is applicable for both the cases. There is hardly any post-construction movement, even in tieback wedge method. In tieback wedge method, of course, it is applicable for extensible reinforcement with the strain more than 1%, and it's active pressure. So I will not go into the tieback wedge method. I will keep my topic specific to only coherent design method. So why and how this method has been evolved and defined. The definition of inextensible reinforcement is quite different in different guideline. This is the extraction from one of the reference given by McGon, is that inextensible reinforcements are those that have rupture strains which are less than the maximum tensile strain in the soil without inclusion. So it's related with the soil strain rather than strain percentage of the reinforcement. But the 1% reference has come from British, which is also very close. I mean, a little conservative, I would say, but very close to what this definition is about. So if you see don't try to scale this graph. It's not to the scale, but just to give you an idea in terms of stiffness of the reinforcement. So of course, steel, as you imagine, the strain is very, very low. So it's quite stiffer. That means it is stiffer than the soil. So what it means is that the force in the steel is mobilized quicker than the soil deformation. Whereas in the geosynthetic reinforcement or synthetic reinforcement, which is the other way, that means the soil deforms and then the force is mobilized. Now, this is just to give you that the stiffness between the two reinforcement, two type of metal, actually really gives us this method of coherent gravity method. Because of the rigidity of the reinforcement, the behavior of the structure as you progress during construction and once it is finished is little different. It's not exactly same. So why coherent gravity method and how it has evolved? So a lot of experiments has been done in 1960s to 70s, and even after 70s with the evolve of load bearing structures, for example, bridge abutments. So a lot of instrumentation has been done, and that gave this concept of bilinear behavior of coherent method. That means when you have a classical tan plus 45 by 2, tan phi plus 45 2 angle of shear plane to a bilinear shear plane, which is shown here in the diagram below. So this is coming from actual experimentations, and it has been also observed that the top portion, top 6 meter of the wall behaves quite rigid, and that's the reason why this behavior is coming up. The line of maximum tension separates this active resistance zone in the RE mass, and I'll go into detail when I'll discuss about the internal stability. And this is the actual instrument, one of the typical tensile stress distribution along the reinforcement, which shows the clear bilinear behavior of the structure by using steel reinforcement. And another reason of bilinear behavior is when you have a rigid inclusion. Now, this definition of this exact bilinear is quite different in different guidelines. I will not go into that much detail. I will focus more on the concept, and little bit like this is the definition given in ASTO, and this is the definition given in and little bit of different in other guidelines like French and British, but more or less it is known as bilinear because you have the shear plane is divided into two linear lines. So this concept is also making this distribution of earth pressure. When we talk about the internal stability, we'll discuss that in detail. So what happens is in the top portion of the structure, which is now defined as 6 meter. Well, technically speaking, it is not 6 meter, it is 120 kPa. That means it depends on the density of the soil. But to simplify, I think in some guideline it is defined as 6 meter. In some guideline it is defined as 120 kPa. Now, generally the soil density is around 20. That's true. But it may not be applicable in all the cases. With some laterite soil where the density is high, this height can be a little less. But of course, our guideline defines it as 6 meter. Well, it doesn't make a major difference in terms of your outputs, but just for better clarity, that this behavior of active and rest is actually depends on the vertical stress, which is limited to 120 kPa. And that's the maximum tension line also. I mean, the tension in the strips or the reinforcement is not constant on this plane. So the line, which is the bilinear line shown, is actually represents the maximum tension line. We'll discuss again. And also, this particular behavior of bilinear is related to the stiffness of the soil reinforcement. By inclusion of stiffness in the soil reinforcement actually gives you a effect of dilation. I hope you understand what it means. It basically the vertical stress with the presence of this inclusion, which is stiffer, as I have shown you the graph in terms of stiffness, it is stiffer than the soil, then there will be increase in the vertical stress with a low surcharge. Now, this is very important to understand that when you have very compacted and high surcharge, higher load, this behavior is not applicable. But with a low surcharge, which is 120 kPa, within 120 kPa, lesser the surcharge, more is this development of this stress, shear stress around the reinforcement. And it has been proven by many research. I don't have to highlight much. And that's why there is an increase in the coefficient of friction also with a low surcharge. This is important to understand that why the structure behave like that. And the behavior is more because of the rigidity of the reinforcement and not just the elongation. So that's why I highlighted this particular behavior of this reinforcement. And this behavior is also there in some other kind of reinforcement which are stiffer other than steel. As I said, it is still not concluded in any of the guideline. So coming to the basic steps, design steps of coherent method, like any reinforced soil structure, it is divided into external stability analysis and internal stability analysis. And you all know what is external, internal. If you don't know, I will again brief you. The reinforced zone, that means the length of the reinforcement and the soil, entire reinforced soil, considered as a gravity structure. And then the external stability, the first assumption that is made is that the entire block of soil reinforcement along with this soil behaves like a gravity, as if it is a rigid concrete block. And then we check the external and internal, the external stability. And so all the checks that we do, sliding, overturning, is very conventional, like we do, and it's based on basic geotechnical fundamentals. The outcomes of coherent method is more towards the internal stability and very little towards the external stability. although that's still debatable, but I will try to give my best, try to explain you why this behavior has been considered in the coherent method. Now, if you see the external stability arc pressure diagram, one is in the left, which is given in the British, and one on the right, which is ASTO. One of the consideration is the principle of Coulomb's earth pressure. That means the earth pressure is acting at an angle of beta. So if you talk about British guideline, this angle is not same as the top slope surcharge, which is there in the ASTO. So even if you don't have any top slope surcharge, this inclination is always there, and it is assumed that there is high friction behind the two reinforced and the retained zone, as you can understand. This, I hope you can see the arrow. So this friction at the back face, interface between the reinforced and the retained zone, has been considered in the coherent method. And I understand that because most of the experiments, why it is like that, in my understanding, most of the experiments are done with steel strips at that point of time. And because steel strips, generally the length of the steel strips are never uniform. You cannot cut the steel strips exactly at the length of, say, 7 meter or 8 meter. There is always plus minus 160. And I understand that probably that variation and the rigidity of the reinforcement generates a very high friction behind. Although the same will be applicable, should be applicable for in other cases also. But some in ASTO, this is again considered as a zero if you have no slope surcharge. Just to give you a brief difference between the two guidelines. So when we do external stability, we actually considered Coulomb's theory. That means the arc pressure is calculated using Coulomb's arc pressure equation. And this is applicable for also with a slope surcharge wall as per ASTO. And as per coherent method, this inclination is applicable even if there is no slope surcharge as per British guideline. So coming to the external stability analysis, the first thing is the check against sliding. So this is like a very conventional standard method. So you have the earth pressure behind, which is giving the disturbing sense is coming from the base, which is the reaction RV multiplied by the friction angle. Now the friction angle can be, there are two way of checking. First, you check with a friction of the foundation soil and cohesion of the foundation soil, and then you also have to check with the friction of the reinforced field soil. So out of the two, which is the minimum, should be considered as a factor of safety for the design. I hope it is clear in a very short, I'm trying to explain because time is a limit, but you can go through the British guideline. There is a quite detailed explanation given how to calculate this factor of safety and also the RV. Similarly, the moment is calculated with a simple physics with earth pressure behind, and then you calculate at the toe. So you calculate the both resisting and the disturbing moment. That gives you the factor of safety, which I think is a simple way to calculate the any gravity structure. Then your bearing capacity, there is a little difference the way we calculate the bearing capacity for a conventional RCC structure or any gravity structure than a reinforced soil wall because of the flexibility of the foundation. So it's not a typical trapezoidal distribution. It is more like a Meyerhof distribution. And that explains in the diagram on the left hand side the actual variation. If you see, there is a concentration of the load which is not exactly at the toe, but almost few meters inside the toe of the structure, and that's because of the moment. And because the foundation is flexible, the stress concentration is more towards the front side rather than the tail end. And it has been simplified in the British guideline, what we use as Mayer of distribution, RV by L minus 2E. And the same principles are applied for calculating all the stresses in the wall. And it's not difficult to, you have to just apply all the physics behind the reinforced soil structure and calculate the moment, calculate the eccentricity, and you can calculate both RV and B. The concept on the left hand side, on the right hand side, sorry, we wanted to explain, because a lot of time we also face this difference of using plate load test for evaluating the foundation bearing capacity. I try to give you a scale of the structure of the Terjagi's distribution. A plate load will never give you even if you apply all the corrections, then also it doesn't give you the correct way of checking the bearing capacity. It's better to just use the Terjagi's equation and check the bearing capacity, and also not by local shear failure, by general shear failure method. Local shear is generally not applicable actually, which is more applicable for a soft foundation. But anyway, in a soft foundation, this kind of structure also requires ground improvement. So most of the cases it is general shear failure which will be applicable. So just try to give you the analogy between the blue and the black to see that even if you apply a lot of correction factor in the plate load, because in the plate load method, the bearing capacity is calculated based on settlement. And in our case, when we design reinforced soil wall, its settlement is not a criteria. It's based on shear strength only. And hence, the bearing capacity that we'll get by using Terjagi's equation vis-a-vis a plate load test, there will be huge difference. So there is no point of doing a plate load test and checking the bearing capacity for RUR. If you really want to check, you can do a confirmatory borehole, and you can use the equations again, and then you can check it. And that's proven. It doesn't require any kind of research on this topic. And then global stability, which is not very common in all the cases, but it is always better to check the global stability. In fact, it is more or less now standard practice in our cases to check the global stability, because actually checking the global stability is more critical when there is a variation of geometry. There are certain bad experiences in our country also, and outside India also, with this issue. When we are designing a wall for highways, now we are building kilometer and kilometer of highways, the site specific considerations are actually lacking, and this global stability can sometimes be very critical when it comes to site specific design. Now, site specific, I mean, like presence of a pond in front of a wall, or presence of a slope, like it is shown on the right hand corner, or building a wall on a field of soil. These are the situation where probably global stability must be done. And of course, your foundation is soft in that case also. So that's very important, and there are certain bad experience, and it must be considered. Nowadays, it's not difficult to do a global stability analysis. This is something which is not coming from any guideline or a book, but this is I'm saying this is coming from the old French ministry guideline. Generally, the length of the reinforcement that we use in the reinforced soil structure, the minimum length, or you can say most of the cases, it is 70% of the height of the structure. And when it is within that range, the behavior is more like a mere hop. But surprisingly, it has been observed that if the length of the reinforcement is increased to, say, minimum the height of the wall, as it is shown here, generally the behavior is more like a general trapezoidal distribution. And of course, it is not written anywhere, but this is a general, and in some cases it is applicable, especially when with a top slope surcharge, this uh, the length of the reinforcement sometimes can be more. Also, in some cases of special foundation condition or global stability condition, you might have a situation, very rare, but still possible. So that is when the trapezoidal distribution is used to calculate the stresses. Sorry, this is done. So settlement, when it comes to the settlement analysis and checking, generally for a standard RUL, it's not required. It is more specific when we encounter differential settlement. Now, the differential settlement, it's something can happen, say, for between the interface of a structure. You have a rigid foundation pile cap, and you have a foundation which is resting on soil. So you can expect a high differential settlement between the two field zone. Probably in those locations, it is advisable to check the settlements. For a normal wall, this is not a major criteria. Yes, if you have a very poor foundation, you must check it because that's give you an idea about how much will be the final height of the structure, because everything is precast, so you need to plan based on your settlement analysis. So that's about all the external stability analysis. Quickly on the internal stability analysis, so you have the tension, adherence, connection capacity. These are the three main checks that we need to perform in the internal stability analysis. So as I have explained the bilinear behavior, this line actually represents the maximum tension line, and you can see on the top right hand corner the variation of the tension along the strip, and then it also differentiate in the bottom two figure is showing you the active and the passive zone. So this is that means that the on the right hand side area, which is shaded area shown, is the active zone, and the zone which is behind the plane is the passive zone, so which is holding the structure together. And that will be important to understand because when we will be doing the internal adherence check, the passive zone is what plays the most important role. So the line of maximum tension is defined in a various format in different guideline, but this is what is there in the British guideline. So I just put the typical values of the plane, what is shown in the British guideline. So when it comes to tension, checking the tension in each layer of the reinforcement, it's a repetitive method of calculation. Now it is not a problem with so much of advanced Excel that we have. It's very easy to calculate. The stresses are calculated. That means you can see on the right hand side using the same principle of Mayer-Hoff distribution, and you calculate the vertical stress, which is sigma v, and then you calculate the tension in the reinforcement by multiplying the coefficient of the earth pressure with the vertical stress and then the vertical spacing. Now the vertical spacing is the spacing which is calculated between the center of each zone of the reinforcement, and that is what is SB, and that's how the maximum tension can be calculated. Now, especially when we are using steel strips, we are playing with numbers. So generally what is done is per meter or per panel width or per two panel width, the total tension is calculated, and then it is divided by the number of strips to calculate the total number of strips. That means if one strip has 40 kilonewton long-term design strength, you divide it by T max, and if your number is coming, say 4.5, you put 5 number of strips, and that is how the strip numbers are calculated. Just to give you a brief T max, of course, for steel this is not applicable. For steel, you calculate based on the ultimate tensile strength of the steel, and you divide it by the ramification factor and a factor of 1.5 to calculate the long-term design strength. While calculating the ultimate strength, you actually reduce the sacrificial thickness. So the steels are galvanized. In India, it is minimum 1000 GSM. Worldwide, it is recommended minimum as 500 to 600 GSM. In Europe, it is 500. In America, it is 600. So it's like that. That after galvanization for 100 years, the corrosion in the steel is very well defined in all the guidelines. So if you want to design for 50 years, 75 years, 20 years, 100 years, you have different corrosion sacrificial thickness. So you just deduct those thickness, and then you calculate the T ultimate, and then you divide it by the factors, you get the design tensile strength in the strips. The behavior again with as I explained in the coherent method, where the pressure diagram, the coefficient of the pressure is varying. That means at the top 6 meter, it is varying from active, at rest condition to active, as you can see in this left diagram. So at the top you have a coefficient of K0, and at 6 meter you have active, and in between it is interpolated, so you can just calculate the exact coefficient, and then you calculate the tension. So this is the very basic principle, as I have explained, applicable for coherent method. And for the pull out, once you calculate the tension by multiplying, as I have explained here in this equation, T max, you multiply the K, so K will be coming from this diagram. If it is below 6 meter, you consider Ka, and if it is above 6 meter, you interpret the K value and you multiply with the vertical stress, and the vertical stress is calculated by this Mayarov distribution, and then you multiply by SV, you calculate the T max. Width can be depend on your method of calculations. Generally, we use 2 panel width. So if each panel is 2 meter, then the calculation width is used as 4 meter. Because we are dealing with numbers, that's why it is not always per meter. It is always calculated depending on the panel width. That's about the coefficient of earth pressure, and there is also a unique difference in the pull-out method. Pull-out method is very simple. I don't have to explain you. You have already calculated the T max from your tensile calculations, and then you check against the pull-out value. So that is calculated by LE. As I have explained, LE is within the passive zone. So you consider only the length of the reinforcement which is beyond this failure plane, and you multiply with the coefficient of friction. I will come to that. It is not exactly tan phi when we are talking about coherent method. And you have the C, which is the surface area. So you have top and bottom. So it is always 2. And then you have sigma V, which is the sum of the vertical stress. So you calculate the sigma B, as I have explained. It is nothing but the density of the soil and the height, and then the width. Because we are dealing with numbers, so each strip width is used. So if it is 50 millimeter, it is 0.05 in meter. So that has to be used, and then you check that the Tmax should be always less than this, and there is overall factor of safety is also there. I'm not going into the load factors and other things. I'm just concentrating on uh, the concept of coherent design method. You can always refer, go through the British guideline. The entire design method is very well explained. And then you check the tension, and that's it. Now the critical part is how you calculate the coefficient of friction. As I have explained that under a low surcharge, under a low confinement effect, there is a dilatancy in the reinforcement, and that leads to a very high um, value of coefficient in the top layers. So when you do a pull out in a direct shear or a direct shear test, you very well understand what exactly I mean by the dilatancy. Now, there is an increase in the stress at this point, and that gives you the higher friction value. And this is what is happening when we are using this kind of reinforcement. Because of the local increase in the stresses, you get a very high coefficient of friction. And generally, the coefficient of friction is depends on different kind of soils. With a high coefficient of uniformity soil, with more gravels, you can get a much higher um, coefficient of friction. And with a silty sand kind of soil with coefficient of uniformity within 2, you get certain kind of coefficient. But it is well proven that this behavior is more or less same. The exact value of coefficient may vary, and there are several tests has been done, not only in abroad, in India, and there are a lot of papers available. If you are interested, please let me know. So which clearly defines that the coefficient of the friction in the top layers are much higher than the normal tan phi value, and that's how this distribution is considered. And when doing the pull-out checks, you basically multiply that coefficient for that respective reinforcement layer, and you calculate the resistance. This is the last topic. Generally, it's not related only with coherent gravity method, but this is my favorite topic. I cannot miss it. Well, this is applicable for whether it's a coherent or tieback, whatever. But the check for the connection capacity is a must. Of course, we all tell, the way I have also said in the beginning that the facing is just a skin element, but facing is also an important element. I mean, if the facing fails, then actually we'll tell that it is a failure of the wall, which is not the case. We geotechnical engineer know that if the facing collapse, it doesn't mean the structure has collapsed, technically speaking. But from a serviceability condition, yes, it's a major failure. So we cannot ignore this concept of connection checking. My idea is to highlight this topic, is to not to show you this because it is there in the British guideline, is that actually the connection load are generally very less, and this is very well proven by instrumentation and by a lot of methods. The load that comes to the facing is less. But then why all these checks? Why there are failures of connections? This needs to be understood very well. This is the most important part, because the behavior of the soil when we are doing the construction is different kind of soil, because soil is not uniform around the world. The test that has been done, and based on which the coherent gravity method has been developed, I'm sure they have used a very nice soil, very good, and there is no doubt. But are we really, when we are building so much a wall, are we really using all the same kind of very good sand? Or no, it's not possible. It's not practical also. Let's be very honest and transparent. I mean, this technology has proved that it can be built with various wide range of soil. Of course, it should not be clay with certain limitations, but even then, the range is quite huge. Now, what happens? Let's try to understand the behavior of the structure as and when we build and as we construct. This will give you the idea what's happening inside and why this is important, why connection is important. So this is a typical construction method. I don't have to explain. You put the panel, you put soil, you keep on building the structure. Okay, that's quite straightforward. And just ensure that the panels are well aligned. Let's stop here and let's check what's happening at this particular. Just focus on this particular layer of soil reinforcement. What's happening as we are building as the construction progressing, the tension in the reinforcement is also increasing, and it's obvious. I don't have to explain why. And you can note that the variation of the tension, there is a little load at the connection, and believe me, it is quite less because this point was challenged by many cases, and there are several examples where after installation we have uninstalled the panels and the structure was standing, so the load in the panel is less. Okay, so then what happens? Okay, as we progress, let's focus on this particular rail of the reinforcement. As we are, the tension in the reinforcement is increasing, the load in the connection is also increasing. It's less than the T max, but it is increasing, no doubt. And then we finish, and this is our typical, I would say, the maximum tension line, and you can see the variation of the tension along the strips, and this is a very till now it is very nice, and we did the wall and the tension is stabilized, the wall is standing. Let's focus what's happening inside, and that will give you some insight how the connection is behaving. So let's talk about this particular reinforcement. So when what's happening, maybe the reinforcement also below connection point. Now when we are using a very good soil, of course there is no problem because it doesn't compress, it is stable and no problem. But what happens when you are using, say, or we are not compacting well, or the soil is got little fine, and then there is a rainfall? What will happen? Even if it is a selected field, even we are compacting, there will be compression. This compression will actually force the soil behind the facing to settle, and it will settle. And there are several walls which I have personally seen when we have installed. We have seen the shape of the reinforcement is exactly like this, which is shown here, the yellow. So what happened is that the panel is actually not settling. So the panel is acting as a very rigid element, and the soil which is settling is acting as a very flexible element. So what will happen if that happens? Obviously, the load at the connection will be not what we know. The load at the connection will be much, much higher. And I'll show you real cases what happens. And that's why most important element which is introduced is, we call them bearing pad. The function of the bearing pad is to address the internal compressibility of the reinforced earth field. We generally know that yes, there is a bearing pad, but we don't know what is the fundamental of this bearing pad. The fundamental of the bearing pad is purely dependent on type of soil and height of the structure. Based on these two elements, actually the bearing is decided. So if you have a very tall structure, say 20 meter, which is very rare, but I want to highlight in this because you guys are going to be on the field someday or the other. Please remember that the bearing pad is not a standard element, which is very commonly known that 20 millimeter thick by a certain dimension. It is not like that. As the wall height increases, as you have different kind of soil, the dimension of the bearing pads are also different. And especially when it goes beyond 15 meter. Actually, it is 12 meter. And in some, if you are doing the construction well, up to 15 meter, it is, using a 20 millimeter, 25, 20 millimeter pad is quite well known. But as you go beyond, this compressibility is very, very critical. And if you don't take care of this compressibility, it will give you a lot of pain and problem. And this is a real example. This is not, this has been proven. So if the internal settlement is high, and now imagine if your connection system is not well designed. Now this wall didn't collapse because it has a very good connection system, and it was designed for the given connection system. But if you have a poor connection system, you can have a disaster. And it is applicable for all kind of facing. It's not just concrete. Even for our weld mesh or gabion, whatever we do, this compressibility has to be taken care of. Otherwise, the stresses at the connection point will be very high, and that can lead to serious problems. And that's why probably all these guidelines and the loads, I'm left with very little time. So that's all about today's presentation. I missed on video. I'll see if we have time. I'll try to show you. But generally, to conclude, yes, coherent gravity method is applicable for inextensible reinforcement, which is now only steel strips or steel element. The method has been developed based on actual instrumentation, and the results are very close to the calculated method. So there is not much of variation. External stability using Coulomb's earth pressure theory, internal stability with K at rest at the top and 6 meter below. Internal friction coefficient, pull-out friction coefficient is also higher than a normal tan phi, and the connection load doesn't change with the method. So these are my conclusions in short. Thank you very much for your patience hearing. I hope you are all awake. I hope I have not and covered all the points. And just to if you have any specific question, anything you want to know into detail, my contact details are here. You can always approach me. I am very much approachable. Maybe I will be a little late in responding or something like that, but be patient. I will definitely respond. So you can always connect me either on email or on phone or any platform as you like. So thank you very much.
Thank you, Atanu. I think the wonderful presentation you made. I think a lot of issues you have taken up and given clarity in those issues actually regarding connecting strength and also the pull-out. I think yesterday only we had a lecture by Anil Dikshit, wherein he presented the pull-out values at low normal stress 50, 100 and 200. And it is very clear to all the students now that the value at 50 kPa normal stress is going to be higher. And then it's lower now. So when you begin the construction, as you rightly said, the pull-out value is higher only. I mean, if you use that pull-out value, let us say for low, conferring a low normal stress, it's high only. But as you keep going up now, that same value is going to come down. That also is a cause for worry for us now. But I thought you will also show your omega connection.
Sorry?
Connection you are using for geo straps or using for metals also? The omega type.
Yes, I can show if you have few minutes.
I think you try.
And I would like to show the video which I have missed.
How long is the video?
Just 2 minutes.
Yeah, Prabhakar, we can spare 5 minutes?
Yeah, sure, sir. Sure, sir.
Yeah. Please go ahead. Atanu, please go ahead.
Sir, give me just 2 minutes. So I'll show you the connection as well as let me share the screen again. Okay, so that's well, we have actually done a lot of experiment on connections. I'll show you live actually. Maybe this one you can see. These are inserts, basically plastic inserts, and steel strip. You can see it's very simple, nothing complicated. It's a nut and bolt connection, and this is also a typical connection that we use for our welded wire mesh system. But what is interesting, you can see the panel. And if you can see, I'm carrying on my hand one of the samples. So it goes inside the concrete. So while casting, we just put inside, and it forms a core within the concrete, and that gives you the strength of the connection. Well, there are several type of connection available. Maybe I missed. I should have put one slide. The first synthetic connection using synthetic strap was used with toggle and loop. Basically, it's a steel loop with a 25 and 32 millimeter dia toggle, and the reinforcement is passed through it. And then slowly, because the corrosion is a big issue, especially in many countries, especially in Middle East, where you cannot actually use steel. It will corrode in 5 years. And so these other type of connection which we have actually developed and also came out, we are using extensively because it's cheaper. We came out with this connection which is called Geomega. Can you see it on my hand?
Just put it down.
Yes, sir.
So this is also, this is like, it goes inside the concrete panel like this, and the strap goes inside and it comes out. So this is also a same concept with the strength coming from the concrete core, and this is which we are currently using because this has got a limitation on the width of the strip. So we can use only up to 50 millimeter. But nowadays we are using 90 millimeter also. So for 90 millimeter, 70 millimeter, or a wider strips, we use this kind of connections, and it can be used for a smaller also. And the core, you can see the concrete, it goes inside. It actually gives you the strength. So there is no steel component. The biggest advantage is, especially when we are building wall, say coastal. We do a lot of coastal application. That means in front of water. There are a lot of apprehension about use this system, but we use quite extensively because there is no steel, so it performs very well for long term. Even if if you have a steel going through, even if a minor crack, see, we are talking about 100-year life. We are not talking about 10 year or 20 year. So even a small crack will corrode the steel, even if you are still passing through the hole. So the idea is to develop a system where there is no steel component, and that's why all this concept has been developed. Sorry, I don't have much more slide I would like to have, but I just want to show you one small video. This one, I hope this time it will play. Let me know whether you can hear the voice. Otherwise, I will speak. Can you hear it? So you can see that
No, sir.
he has used.
No, sir.
Yeah. Yeah. So I just wanted to demonstrate the same principle what I have explained. There is a link available in YouTube, and LinkedIn also. I got it from there, and I thought it is very
Yeah.
informative for students to visualize that how the same principle of this boulder concept can be applied to a soil also, because it works through friction. That's all, sir, from my side. Thank you.
Thank you, Atanu. I think we're happy that you could spare some of your time. I know you people are very busy and
Sir,
you have to
pleasure,
really
sir.
take the time for the presentation. It's a pleasure for us to hear you. And I look forward to your presentation again, probably in April, wherein we'll have a webinar by you also, wherein we'll actually talk of case histories. And the other day I was looking at my office. You remember you have given me one book also. Prairie Army, 50 years of
Right, sir,
the
right.
subject. It's a wonderful book.
Yeah,
Maybe when I go to Haiti, if I go there, I will leave the copy there, because it's more useful to the students also.
yes,
The
yes.
process development.
No,
is
I
there
will
actually.
send you one more, sir. I'll send you one more. You keep it. I'll send one more to the IIT. No problem.
Yeah, it's wonderful actually. And maybe you should also maybe send a copy of BBA, at least one certificate or something like that, for one system.
Okay,
You
okay,
have
no
BBA,
problem.
because they should
Yes,
know
yes.
this actually.
Yes,
See,
yes.
the only one thing I want to tell about the reinforcement is that it is a original reinforcement actually, wherein it's complete. That means the design of the system, the strips and the connection and everything else actually is done by the same company. It's not that I buy something else from somebody and then assemble it here or something like that. No, the total responsibility taken by them. That is why they're able to do wonderful work. And from concept to construction and of course servicing for next 120 years is not a joke. I'm sorry, it's not a joke. There's a very correct word actually. And doing in many circumstances, apart from what do you call Gulf countries now, they're able to waterfront structures. After all, we know normally the steel is affected by salt water, and even then they're able to do the structures actually for many kinds of waves and other kinds of things. Is something very challenging, and that they're able to do because it's a truly international company. I have a lot of soft corner for them, but when once you do one good thing, naturally it costs you. So on cost basis per se, it may not always work out to the clients, but the clients are also these days recognizing the value of the system and the way in which it's constructed. And in fact, almost all the works in the beginning in the country, like what you have told earlier to me, the work which is there in entry to Jaipur, from Delhi. What's that? Maybe bypass something that outer ring road. I think there is wonderful. I think it really stands tall. I mean, there are many structures. We have one in Bikaji complex in Delhi. When you come to IIT from outer ring road, from ring road actually. So there are many things which stand apart actually. I mean, then you have to find out who has done this work, who has done this work now. I think that's where the technology actually goes further now. It's not by canvassing alone. It's not by meeting clients alone. It is by the structures which are there now. I think they're wonderful structures. I think we should study more of that now. As you said, now he didn't give the equations because they're already there in the COP. But I can tell you that he is familiar with every word there. He's helping us a lot actually making the COP for BAS now. I think his contribution is wonderful because he goes on and the final thing is that unless he allows us to publish it, we will not publish it also because
No, no.
no. What I'm trying to say is that he goes through patiently every bit of it and then okay, sir, this is right. And he will tell you convincingly why it is wrong also. So then they know the way accept him now. But we will also not accept it. We will also keep discussing and then meetings and things like that. But I think his contribution is very valuable. And also, most of the things which he's saying is not always public information. Please remember this now. He's shared many things which are basically not told to everybody, but being students, I think, and we have trust in IIT Gandhinagar and IIT Gandhinagar students now, you should use it for positive image now, for doing better work. I think that is the spirit in which he works and the company works, and we also work like that only. Thank you, Atanu. We look forward for case history presentation, and I think we're slightly more convinced. Thank you, then.
Honored, sir. Honored. Thank you so much, sir. Thank you for your kind words. Thank you, sir. Bye-bye.